Hello everyone. Welcome to Brilliant Group of Institutions, Qatar. This session is for the discussion of very important MCQ questions in preparation for your CBSE Grade XII examination. The first chapter we're going to discuss is on relations and functions. It's a very important chapter. There are a lot of concepts based on this chapter and we have to go through them one by one. I've tried to include almost every concept that is possible to come from this chapter. So let's go straight to the questions. Question number 1, my dear students. Question number 1. The relation R in the set A is equal to 1, 2, 3, 4 is given by R is equal to 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3 and 3, 2. We are supposed to verify whether this function is reflexive, symmetric, transitive, all these conditions. So I want everybody to look at what is given to you here. The set is A is equal to 1, 2, 3, 4. The set A is equal to 1, 2, 3, 4 has to become reflexive if for every element in that set, there should be a reflexive pair inside the relation. Look at the elements one by one. 1, 2, 3, 4. The reflexive pairs for the element 1 is 1, 1 and for element 2 is 2, 2. Okay, for element 3, it is 3, 3 and for element 4, it is 4, 4. It is very clearly visible that for every element inside the set, there is a reflexive pair inside the relation. So, what can I conclude from that? I can say that for every x that belongs to the set A, there is an ordered pair x comma x which belongs to the relation R. Yes. So I can say that R is reflexive. R is reflexive. So if R is reflexive, I will obviously look at my options. I can see that option C says R is not reflexive. So I will reject option C. Reject option C because R is not reflexive in option C. Now let's look at symmetric. Let's look at the condition for symmetric. What does the symmetric condition say? If I have an ordered pair x comma y which belongs to R, then y comma x also should belong to R. Then only R is going to become symmetric. Just try to understand, when you say R is symmetric, there will be a lot of confusions to many students when you try to think in terms of whether it is symmetric. Just try to learn the condition in requirement for a relation to become not symmetric. For a student who is preparing for boards, you just need to know when the relation is not symmetric. Look at the condition. If ordered pair x comma y belongs to the relation R, but the ordered pair y comma x does not belong to R. Does not belong to R. Learn it, my dear students. Does not belong to R. Ordered pair y comma x does not belong to R. This is the situation where R is not symmetric. I want everybody to understand only this concept for not symmetric. Okay, so that is the only reason for a relation to become not symmetric. Every time else it is symmetric. Every other condition makes it symmetric. So x comma y is inside the relation, but y comma x is not inside the relation. That is the only reason for not being symmetric. Now look at the statements, my dear students, one by one. First one, reflexive and symmetric but not transitive, reflexive and transitive but not symmetric, and equivalence relation. So let me check if I have an x comma y inside the relation R. Look at it. I do have an x comma y inside the relation R. See that? Can you see 1 comma 2? Can you see 1 comma 2? So I will say here 1 comma 2 belongs to the relation R. But do I have a 2 comma 1? You can see that the 2 comma 1 is not there in the relation R, but 2 comma 1 does not belong to R. 2 comma 1 does not belong to R. So I can say that R is not symmetric. R is not symmetric. R is not symmetric. So, which options will I look at now? He is saying that the first option says that R is symmetric. R is symmetric. It is wrong to say that. And I will reject option D also, because option D says it is an equivalence relation which is reflexive and symmetric and transitive. So I will reject option D also. So my answer is option B. So which is my answer, my dear students? My answer is option B. Is it clear, everybody? Yes? Okay. Let's go to the next question now. All of you. Read the next question, please. For real numbers x and y, define the relation between x and y if and only if x minus y plus root 2 is an irrational number. X minus y plus root 2. So if I'm taking two elements x and y, then x minus y plus root 2 is an irrational number. Okay, is an irrational number, say it belongs to T. So something which is irrational is always going to have the square root of a number which is not a perfect square. The square root of a number which is not a perfect square. So let's try to understand. Okay, so let's see if it is reflexive. So what does reflexive say? For ordered pair x comma x. So I'm considering the ordered pair x comma x. Let's see if this ordered pair exists inside the relation R. Then what is going to be happening to my condition? It is going to become x minus x plus root 2. Why x minus x plus root 2? Because here in place of x, you have x. In place of y, you have x again. Try to understand. So this is x and this is my y. Okay, this is my y. So what is x minus x plus root 2? I am getting my answer as the square root of 2. The square root of 2. So obviously, square root of 2 is an irrational number. Yes. So therefore, can I say whatever value I put for x, my relation R is obviously reflexive. Obviously reflexive. So I need not try to do everything else. Why? Because option D says none of these. If option D was saying it is an equivalence relation or all of these, then you should have to check for symmetric and transitive. I don't have to go further because I got that this relation is reflexive. So my answer is option A. Option A, which says that the relation R is reflexive. I hope everybody is clear with question number 2. Okay, so let's move on to question number 3. Move on to question number 3. Question number 3 says the relation that exists between A and B is A is the brother of B. A is the brother of B. And the conditions given here are symmetric and transitive. Look at the options. They are not concerned about reflexive here at all. They are only concerned about symmetric and transitive. Let's try to understand what is the condition for being symmetric. So I would say that ordered pair, I would try to say that ordered pair A comma B belongs to the relation R. Ordered pair A comma B belongs to the relation R. Then I can easily say that A is the brother of B, right? A is the brother of B. That is what is said in the condition. A is the brother of B. Now, is the symmetric pair B comma A also in the relation? Let us try to think backwards. If A is the brother of B, is it necessary that B should be the brother of A? No, it is not necessary that B should be the brother of A. So B may be, but B may be the sister of A. B may be the sister of A. Try to understand, my dear students. If A is the brother of B, it need not be the reverse always. B need not be the brother of A. B may be even the sister of A. Yes, therefore, Therefore, I can say that the ordered pair B comma A need not be an element in the relation R. B comma A need not be an element in the relation R. So, not symmetric. It is not symmetric. It is not symmetric. That is easy now. Yes. So, if it is not symmetric, I can obviously reject which all options? Option D rejected, which says it is symmetric and transitive. Okay. Option A rejected, which also says it is symmetric. Now, my condition is to check whether it is transitive or not. What is meant by transitive? Transitive, we haven't discussed about transitive in the previous question also. Let us try to understand what is meant by transitive. I would again try to say not to think about when it is transitive. Just think when it is not transitive. See here, A comma B and B comma C belongs to R. This is what I want every one of my students to understand. For transitive condition, the second element of the first pair and the first element of the second pair should be equal. Only these kind of pairs are used for transitivity of a relation. If I have a pair called AB and a BC, but I do not have a pair called AC. I do not have a pair called AC. Okay, then I would say that my relation R is not transitive. R is not transitive. Try to understand this. This is the only case. This is the only case where the relation is not transitive. I have an AB, I have a BC, but I don't have an AC. Every time else, R is going to be transitive. This is the only case when R is not transitive. Try to understand. Keep that in mind, what I'm saying now. Okay, now let's try to analyze. AB means A is the brother of B. BC means B is the brother of C. So if A is the brother of B and B is the brother of C, what is going to be the relation between A and C? What is going to be the relation between A and C, my dear students? It is very, very easy to tell. A brother of B, B is the brother of C, and then obviously A is the brother of C. A is the brother of C. So here I can say A is the brother of C. Yes, A is the brother of C. A is the brother of C. So I can say AC belongs to the relation R. AC belongs to the relation R. Therefore, R is transitive. R is transitive. So R is not symmetric, but R is transitive. Look at the options here. B, transitive but not symmetric. Correct option. Transitive but not symmetric. Very easy question. Okay. Now let's go for the next question, my dear students. Next question is defining the set L of straight lines in a plane, and the relation between the straight lines is that if and only if the lines are perpendicular to each other. L is perpendicular to M. L is perpendicular to M. So if I talk about a line and to itself, reflexive pair is always a relation which exists from an element to itself. L comma L. So can a line L be perpendicular to itself? L is not perpendicular to itself, right? L is not perpendicular to L. L is not perpendicular to L. Yes. So can I conclude that implies R is not reflexive? R is not reflexive. Can everybody understand that? That R is not reflexive. R is not reflexive. So obviously option A is wrong. Option A is wrong. Let's try about symmetric now. Let's try about symmetric. For symmetric pair, it should be two lines. The first line and the second line. L1 comma L2. So you can just say that L1 comma L2 belongs to R. Then you can diagrammatically represent that as L1 is a line, Yes, which is perpendicular to L2, another line. L1 is a line which is perpendicular to L2, another line. Okay, then you think backwards, is L2 perpendicular to L1? Yes, if L1 is perpendicular to L2, obviously L2 is also perpendicular to L1, right? So if for every pair which looks like L1 comma L2, the symmetric pair L2 comma L1 also belongs to R, therefore R is symmetric. R is symmetric. Okay, R is symmetric. So I can obviously go for option B as the correct answer, which says it is symmetric. Okay, why did I not go for checking transitive? Because again, the same reason, option D is none of these. If they would have said about any other conditions, I would have checked it, because it's purely clear that this relation is symmetric. So I have to go for option B. I have to go for option B, and there is no other option which tells me that it is symmetric as well as something else. So I don't have to check it. I don't have to check it. So that question is done. So let's go for the next question, my dear students. Look at the next question, please. It says a relation R on the set 1, 2, 3 is defined by R is equal to 1, 2, then R is reflexive, R is transitive, R is symmetric, none of these. Okay, so it's again defined on the set 1, 2, 3. This 1, 2, 3 set is a very, very important set, my dear students. This 1, 2, 3 set is a very, very important set. They like asking questions with this set very often. Even if this change the numbers, this 3 number set is a very important set in reflexive, symmetric and transitive. Let's try to understand. They're saying that my set A, I'm calling it A as 1, 2, 3. And I'm trying to check whether it is reflexive. According to the condition of reflexive, for every element inside the set, the reflexive pair should be inside the relation. What are the reflexive pairs that you see for the set 1, 2 and 3? The reflexive pair is going to be 1, 1, 2, 2 and 3, 3. Okay, 1, 1, 2, 2, 3, 3. Now, look at the relation R. All of you look at the relation R in the question. Do you have a pair called 1, 1, 2, 2 or 3, 3 in it? You don't have it. Yes, I don't have a pair called 1, 1, 2, 2, 3, 3. So I can say R is not reflexive. R is not reflexive. What is the reason? You can say a simple reason for those students who are listening this for the first time. For every element, say consider 1. 1 belongs to A. But the reflexive pair 1, 1 does not belong to R. The reflexive pair 1, 1 does not belong to R. So R is not reflexive. So not reflexive. Not reflexive. Let's talk about symmetric now. Let's talk about symmetric. What does symmetric say? What is the symmetric condition? For not being symmetric, I told you in a few questions back, not being symmetric means if I have a pair x, y and I do not have a pair y, x. Keep that in mind. Do I have a pair x, y here? Do I have a pair x, y here? Yes, I do have a pair x, y. What is it? Here 1, 2 looks like x, y, which is an element of the relation R. Yes, but do I have a symmetric pair inside? No. So I can say, but 2, 1 does not belong to R. 2, 1 does not belong to R. Yes, 2, 1 does not belong to R. So I can say not symmetric. Not symmetric. Okay, so again, we cannot come to a conclusion still now because they said not symmetric. Yes, not symmetric. Now let's try for transitive now. What is the condition for not being transitive? What is the condition for not being transitive? One simple condition. What is it? I have a pair called AB. I have a pair called BC, but I do not have a pair called AC. Yes, what was the condition? You can just go back to the question before this. It is clearly mentioned for what is the condition for not being symmetric. Not being transitive. Keep in mind, not being transitive. I have a pair called AB and BC, but not AC. So let's look at it. I have a pair called AB. Yes. Let's see, I have a pair called AB. I have a pair called AB. Fine. Now, is there a pair called BC from this? Do I have a pair called BC from this? No, I do not have a pair called BC. I do not have a pair called BC inside. So it does not satisfy the condition for not being transitive. Once again, what is the condition for not being transitive? AB and BC should be there. AB and BC should be there. Then, if AC is not there, then it is not transitive. So, all the other conditions which is opposite to or which is not satisfying this not transitive condition is definitely transitive. So, what is it? AB is there, but BC is not there. It is not satisfying the condition to become not transitive. So, then I can say, therefore, R is transitive. R is transitive. This is the most confusing thing for many students when it comes to a board exam. Why is it transitive? Remember, I would want you to always think in terms of not being transitive. So, is it transitive? Yes, definitely it is transitive. So, what is my answer? My answer is option B, which says this relation R is transitive. Okay? Please keep in mind, it's a very, very important question. Okay? Okay? To make that concept more clear, let's see this relation now. Same thing, I've included one more element, that's all. 1, 2, 3, 4. Again, obviously, not reflexive. Yes, you can see this. 1, 2, 3, 4. It is not reflexive. Why? Why is it not reflexive? Again, the same old reason. Why is it not reflexive? If I take an element 1, which belongs to my set A, but the ordered pair 1, 1, the reflexive pair does not belong to R. Does not belong to R. So I can say that it is not reflexive. It is not reflexive. Is it clear, everybody? So I will reject the option A, which says it is reflexive. Okay. Now let's again think about symmetric, please. Let us again think about symmetric. What is the condition for not being symmetric? What is the condition for not being symmetric? What is the condition again? I have a pair called 1, 2. I have a pair called 1, 2, which belongs to the relation R. But do I have the symmetric pair 2, 1? Do I have the symmetric pair 2, 1? I don't have it. I don't have the symmetric pair 2, 1. So I will say that the symmetric pair 2, 1 does not belong to R. Does not belong to R. So I can obviously say not symmetric. What is the answer? Not symmetric. I'm going the correct way because I want everybody to understand the concept also of this question. So it is not symmetric. It is not symmetric. But what about transitive? What about transitive? Is it transitive? What is the condition again for transitive? If I have an ordered pair A, B and an ordered pair which starts with B to another element called C. A to B and B to C. The most important thing about being transitive is these two elements should be equal. These two elements should be equal. Look at the pair that is given to me in the question. I have two pairs which looks like AB and but not BC. Okay, this pair over here, this is called AB, but this is not BC. This is not BC. Get it? It is not BC. So here BC does not belong. BC does not belong. BC does not belong to R. Right? So this condition for transitivity is automatic. Not being transitive. Again repeating it. Again I'm repeating it. Not being transitive. The condition for not being transitive is failing. So it is going to be transitive. Okay. Therefore R is transitive. R is transitive. Because I cannot prove that it is not transitive. If I cannot prove that it is not transitive, obviously it is going to be transitive. This is how it's a quicker approach for an MCQ question. If you go to search for whether it is transitive or not, it is going to be always confusing. You search for whether it is not transitive or not. That is an easier approach for these kind of questions. So, my dear students, the answer is option B. The answer is option B. Okay, let's go for the next question now. Let's go for the next question, all of you. Okay, fine. Now this question is not that important for MCQ. You can just by heart it. The answer is 5. You can by heart it. The answer is 5. A set which contains 3 elements 1, 2, 3. What is the maximum number of equivalence relations which is going to be formed using the set 1, 2, 3? Okay, so now the answer is 5. Yes, but we need to understand why it is 5. And this, I introduce this question here simply to explain 2 more questions which is going to come after this, which is a very, very common question nowadays in your examinations. Okay, so let's try to understand which are these 5 equivalence relations. Actually, there is no particular formula to find it. It's all just a manual method. We have to write it down and check. Write it down and check. So I'll tell you which is the first equivalence relation which I can form from this set. The first equivalence relation which I can form from the set, R1. R1 is going to be ordered pair 1, 1, ordered pair 2, 2, and ordered pair 3, 3. Since I'm forming this relation from the set 1, 2, 3, I have to have all the reflexive pairs 1, 1, 2, 2, 3, 3 to make it reflexive. And what is the condition for not symmetric? AB is present, but BA is not there. I will write that over here. What is the condition for not symmetric? Okay, keep this in mind. What is the condition for not symmetric? AB belongs to the relation R. AB belongs to relation R, but not BA. BA does not belong to R. BA does not belong to R. This is what I want to keep in mind. Now look at it. Is it symmetric? Obviously it is symmetric. Why? Because it is not satisfying the condition to become not symmetric. Is it satisfying the condition to become not symmetric? According to condition of not symmetric, there should be AB but not BA. Is there an AB? No. So it is obviously not symmetric. This is the confusing part we have to be very clear with. Why is it symmetric? Because it is not symmetric. Why is it symmetric? Because it is not satisfying the condition to become not symmetric. It is not satisfying the condition to become not symmetric. What is the condition to become not transitive? What is the condition to become not transitive? The condition to become not transitive is AB and BC. Both these pairs belong to R. AB and BC belong to R, but AC does not belong to R. AC does not belong to R. So what is the condition to become not transitive? So look at this. Do I have a AB and a BC to prove that it is to be satisfying the condition of transitivity? No. If I don't have a pair like that, obviously I can come to a conclusion that it is transitive. That is why this is an equivalence relation. Because I cannot prove that it is not transitive. I cannot prove that it is not transitive. So if I cannot prove it is not transitive, it is going to be a transitive relation. Okay. Now that is the first relation I'm going to say. Now R2. R2 is going to be, now I can go quickly. 1, 1, 2, 2, 1, 1, 2, 2, 3, 3, and I'm introducing a pair called 1, 2, which looks like AB, and I have to make it an equivalence relation by making it to BA. So 1, 2, and I'm going to introduce the pair 2, 1. 1, 2, to make it symmetric, I'm going to introduce the pair 2, 1. Okay, so 1, 2, 2, 1. Now is it symmetric? Yes. Is it reflexive? Yes. Now is it transitive? Don't look at it and say if it is transitive or not. Just look at it and say if it is not transitive. Just look at it and see if it is not transitive. Do I have an AB? Yes, 1, 2. Do I have a B to C? C is some other element. Do I have a BC? No. So AB and BC should be there. There is no BC. So obviously it is not being proved to be not transitive. You cannot prove that it is not transitive, then it is transitive. So this is a equivalence relation number 2. Let us talk about a third equivalence relation, R3. R3, same way. 1, 1, 2, 2, 3, 3, and I'm going to introduce another pair called 2, 3. So then to make it symmetric, I will say 3, 2 as well. The same reason for why R2 is equivalence, R3 is also equivalence. Now, is there any other pair left? One more is there. Yes, R4, 1, 1, 2, 2, 3, 3, 1, 3. Yes, the pair between 1 and 3. Then to make it symmetric, I will say 3 and 1. So R4 is also an equivalence relation. R4 is also an equivalence relation. So 4 equivalence relations, is it? One more. I have to find one more. The fifth one is completely all the pairs that we discussed till now. 1, 1, 2, 2, 3, 3. Then I would put 1, 2 with 2, 1. Then 1, 3 with 3, 1. And then 2, 3 with 3, 2. 2, 3 with 3, 2. These are the 5 equivalence relations which can be defined from the set 1, 2, 3. Now, you have to do this manually. Yes, and please learn it that it is 5. I'm again repeating, I'm teaching you this simply for explaining something else. Okay, so let's go for the next question, which will very clearly tell you why I'm teaching you this. Look at the next question, please. A is equal to 1, 2, 3 and the number of relations which are containing 1, 2 and 1, 3 which are reflexive and symmetric but not transitive. Which are reflexive and symmetric but not transitive. So you know how to already write the relation, right? So I'm going to write the first relation which is reflexive. So it has to be reflexive means it should contain 1, 1, 2, 2 and 3, 3. Yes. Now, which are reflexive and symmetric, which should contain 1, 2. Because 1, 2 is compulsory with 1, 3, to make it symmetric, I need to introduce 2, 1 and 3, 1. To make it symmetric, I have to introduce 2, 1 and 3, 1. So this is the pair or this is the relation which is reflexive, and now I have included 1, 2 and 1, 3 which should contain, it is not an option, it should contain 1, 2 and 1, 3. It should contain 1, 2 and 1, 3. It is not an option. 1, 2 is there, 2, 1 is there. Symmetric. 1, 3 is there, 3, 1 is there. It is symmetric. But I have to see whether this is transitive or not. Whether this is transitive or not. Let us find a pair which looks like AB, BC, but no AC. AB, BC. Okay. Now this is something which most of you will not be able to find out. Look at this now. 1, 3 and 1, 3. 1, 3 is there? Yes. Okay. 1, 3 and let's see. 1, 2, 1, 3. 3, 1. 1, 2. Okay. This is the pair, my dear students. 3, 1 and 1, 2. All of you look at it. 3, 1, 1, 2. 3, 1 can be understood as AB. Yes. Then next take the pair 1, 2 which can be understood as BC. Yes. AB is there. BC is also there. Okay. Both of them belong to R. AB and BC belong to R. So now it is open. Now it is open. Let's check. Which is AC? Which is AC? AC is going to be 3, 2. Yes, but 3, 2 does not belong. 3, 2 does not belong to R. 3, 2 does not belong to R. So if 3, 2 does not belong to R, can I say R is not transitive? So this R1 is not transitive. R1 not transitive. R1 not transitive. Yes. Now you have seen in the previous question that the relation which can be made without these elements is going to be R5. if any other new element or any other new relation which can be made with these 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 1, 3, 3, 1 is R5, which has to contain 2, 3 and 3, 2, which makes it transitive. So I cannot find any other relation which is going to be reflexive and symmetric but not transitive. Sometimes students will argue, sir, why not simply put a 2, 3 here? Isn't it not another relation which is reflexive and symmetric but not transitive? Simply putting a 2, 3 is not going to create a problem because 3, 2 is the only problem, right? So why not put 2, 3 here? If you put 2, 3 here, it is no longer symmetric. It is no longer symmetric. Get it? If 2, 3 comes, you need a 3, 2. If 2, 3 comes, you need a 3, 2. And if you put 3, 2, it becomes transitive. I want a relation which is not transitive. I want a relation which is not transitive. Okay. So what is my final answer? How many relations can I form? I can only form one relation. That is why I discussed that question now. Okay. Why you understood why I'm discussing the maximum number of equivalence relations which can be formed. Manually, I have written all the 5 equivalence relations just to explain this concept. This is very, very important. Very, very important question. Okay. Going to the next question, students. Look at it. A is equal to 1, 2, 3. Then number of equivalence relations containing 1 and 2. 1, 2, already done, right? Already done. How many equivalence relations contain 1, 2? Look at it. How many equivalence relation? You can see this. There is a 1, 2 over here. Yes. There is a 1, 2 over here. From the set of elements 1, 2, 3, how many equivalence relations can you form with the ordered pair 1, 2? With the ordered pair 1, 2. How many can you form? You can form, how many? Come on. How many can you form, students? You can form only 2 equivalence relations. You can form only 2 equivalence relations. This is very, very important. Please mark it. It's very, very important question. Please study this. Okay. So now, very clearly, I have written all the 5 equivalence relations which can be formed from 1, 2, 3, and I have said that only 2 of the equivalence relations is going to contain 1, 2. Only 2 of the equivalence relations contain 1, 2. Okay. Next question. Now, A and B are finite sets containing m and n elements. The number of relations that can be defined from A to B is number of relations. It's actually 11th standard concept. So let's try to understand what is a relation. What is a relation? Relation is simply the subsets of A cross B. Yes, because it is the relation that is defined using the sets A and B. Yes, 2 sets. So the Cartesian product of A and B is going to give me the subsets which is going to be required for using the formation of a relation R. Okay. Next, what is the formula for number of subsets? Again, a 11th standard concept. What is the formula for number of subsets? 2 raised to n. 2 raised to n. What is n? N is the number of elements in the set. Yes. N is the number of elements. Number of elements. Number of elements in the set. Number of elements in the set. So here my set is A cross B. Here my set is A cross B. Therefore, what is going to be 2 raised to n? That is equal to 2 raised to number of elements in A cross B. Number of elements in A cross B. So here my set is A cross B. So what is going to be the number of elements in A cross B? Again, 11th standard concept. Number of elements in A cross B is number of elements in A multiplied with the number of elements in B. What is the number of elements in A and B? It's given to you, m and n. That is going to be 2 raised to m into n. 2 raised to m into n. So you can easily learn this as a formula. So number of elements in, number of relations that can be formed as 2 raised to mn. By heart it. If you want to, you can by heart it. 2 raised to mn. Okay. So that's easy. Going to the next question, students. Okay. In the next question, it is saying that A is a finite set. A is a finite set, and you're defining this set using defining a relation using n distinct elements. You're defining the relation using n distinct elements of A. So here your relation is the subset of not A cross B, it is the subset of A cross A, because here the relation is defined on a single set. So the elements are relation between the same elements of the same set. Okay, that is, if I take an element X and an element Y, both of them should be obtained from the same set A. So I am forming this relation as a subset of A cross A, Therefore, what is the number of relations? What is the number of relations? Is equal to 2 raised to number of elements in A multiplied to the number of elements in A. That is equal to number of elements in A is n into n. N into n is n squared. So what is the number of relations from a set A to itself? The number of elements is going to be 2 raised to n squared. That is option C. 2 raised to n squared. That is option C. Very easy question, similar question. That's why I did once again a question like that to make it more clear. Okay, next, they're saying that R is a reflexive relation. R is a reflexive relation, and I have to take this relation R from the elements of a set A which contains n elements. Elements of a set A which contains n elements. Now let's try to understand. If A is the set of n elements, for example, I'm saying the n elements are 1, 2, 3, etc. n. Then definitely R has to become reflexive only if I have these pairs 1, 1, 2, 2, 3, 3, etc. up to n. Only if all these pairs exist, this becomes reflexive. So mark it, everybody. Why is it reflexive? This is going to be reflexive because I have all these pairs to make it reflexive. And how many pairs are there? How many pairs to make it reflexive? N pairs. How many pairs? Because there are n elements, then n pairs is required to make it reflexive. But is this the only relation which is going to become reflexive? Can I make it reflexive by adding some more elements? Definitely I can. You just simply need to add some more pairs like this, 1, 2. If I had a pair called 1, 2, it's still reflexive. It is still reflexive. If I had a pair called 2, 3, it is still reflexive. So it can keep going like this. And they're saying that the total number of pairs, all of you, the total number of pairs that is inside this, the total number of pairs that is inside this is m pairs. So my dear students, so what is the condition for a relation to become reflexive? If the set has n elements, and the relation has m ordered pairs. The relation has m ordered pairs. The condition is very simple. Therefore, the value of m should be greater than or even equal to n. Yes, I can say that 1 to n is a reflexive relation. Yes, but if I add more also, it still stays reflexive. So I can say the number of ordered pairs m inside the relation should be greater than or equal to n. Answer is option B. Answer is option B. M is greater than or equal to n. A very easy question. Yes? Okay. So let's go to the next question now. In that, I forgot to say something here. See this. Sometimes there could be a question based on this also. Like if there are n elements in the set. If there are n elements. If a relation R is defined on a set containing n elements. Then number of reflexive relations is going to be 2 raised to n into n minus 1. 2 raised to n into n minus 1. To make it more clear, let's say that if this n is 3, then the number of reflexive relations is going to be 2 raised to 3 into 2, that is equal to 2 raised to 6. 2 raised to 6 reflexive relations can be formed. What about symmetric? 2 raised to 3 into 3 into 4, 3 into 4 divided by 2. 3 into 4 divided by 2, that is equal to again 2 raised to 6. This is also 2 raised to 6. So a set containing 3 elements, it can form maximum of 2 raised to 6 reflexive relations and 2 raised to 6 symmetric relations. Okay? Easy answer. Maybe a 1 mark question. Please by heart the formula. What is the maximum number of equal reflexive relations? 2 raised to n into n minus 1. Maximum number of symmetric relations. I told you there is no formula to find the maximum number of equivalence relations, but there is a formula to find reflexive and symmetric relations. I wouldn't say that it's going to be very, very important because it is not mentioned likewise in your CBSE textbook, NCERT textbook, but if you learn it and if a question comes from this, you can easily score marks. Okay? Fine. Next. Consider the relation R defined on the set A is equal to 0, 1, 2, 3, 4, 5, 6, 7 and the relation R is defined in such a way that R consists of ordered pairs A, B. R consists of ordered pairs A, B, okay, in such a way that 2 divides A minus B. The difference of A and B, okay, the difference of A and B is going to be an even number. A minus B should be an even number. And they're asking me to find the equivalence class 0. They're asking me to find the equivalence class 0. What is meant by equivalence class? What is meant by equivalence class? It's very easy to do this. Equivalence class of 0. Equivalence class of 0 is given by square bracket 0, that is equal to, it is all the ordered pairs. All the ordered pairs A, 0. All the ordered pairs A, 0 such that 2 divides A minus 0. 2 divides A minus 0. What is A minus 0? No doubt. What is A minus 0? A minus 0 is going to be A, right? So I have to pick out those numbers A. I have to pick out those numbers A in such a way that I'm going to get the answer which is going to be divisible by 2. Yes, pick out the numbers A which are divisible by 2. Therefore, the equivalence class, okay, fine. Let me tell you something here. Equivalence class is not ordered pair. Equivalence class is the set A. Equivalence class is the set of A such that 2 divides A minus 0. 2 divides A minus 0. So, what is the equivalence class of 0 now? What is the equivalence class of 0 now? Equivalence class of 0 is going to be all the values of A in such a way that 2 divides A minus 0, which is A. So, answer is 0, 2, 4 and 6. What are the sets? 0, 2, 4, 6. Option D. Option D. Equivalence class is a very common question, and this perfectly same question is the most probable question in your CBSE examination. Okay, grade 12 examination, most probable question, 2 divides A minus B. Or they could simply change the condition, that is all. So you have to find an element which is going to be satisfying that condition, that is it. Okay, got it? So next question please. Yes, R is an equivalence relation on A, then R inverse on A is what? It's again a property. Any equivalence relation R, then R inverse is also equivalence. It's a property, you can just learn it. R inverse also is equivalence. It's a proof question, so we don't have to do it. Learn it. Equivalence relation. R inverse is also an equivalence relation. If R is equivalence, R inverse is also equivalence. If R is reflexive, R inverse is also reflexive. If R is symmetric, R inverse is also symmetric. If R is transitive, R inverse is also transitive. Keep in mind, finished. Okay, so whatever, depending on whatever is given to you, if R is equivalence, R inverse is equivalence. If R is said to be reflexive only, then R inverse is also reflexive only. If R is symmetric, then R inverse is also symmetric only. And if R is transitive, then R inverse is also transitive only. So I can say that R inverse is an equivalence relation. The inverse of a relation. The inverse of a relation is a question from 11th standard, and I'm connecting that to a question of equivalence of a relation. Okay? Next question. Yes, the relation greater than denoted on the set of integers. Is it symmetric? Is it reflexive? It is transitive. Okay, let's check it one by one. The first one, is it reflexive? Is it reflexive? I would say not. I would say not. Why? X comma X implies X is greater than X, which is wrong. It's false. X cannot be greater than itself. An ordered pair X comma X will come in the relation R, then only it is reflexive, right? But can X comma X come inside this relation R? No, it cannot. Why? Because it can come inside the relation R if and only if it can be greater than itself, right? It cannot be, right? X cannot be greater than itself, so it is not reflexive. Not reflexive. So option B is gone. Is it symmetric? Is it symmetric? Next one, is it symmetric? Again, I would say not. Again, I would say not. Why not? Why not symmetric? Okay, let's see this. What is the condition for not being symmetric? I would say a pair 2, 1 belongs to R. What is the condition for being not symmetric? 2, 1 belongs to R. Why? Because, what is the reason for 2, 1 belongs to R? Because 2 is greater than 1, no doubt. 2 is greater than 1, but 1, 2 does not belong to R. 1, 2 does not belong to R. Therefore, R is not symmetric. R is not symmetric. Why is 1, 2 not belonging to R? Simple reason. 1 is not greater than 2. 1 is not greater than 2. So it is not symmetric. It is not symmetric. So the last one is none of these. So I have to check for transitive also. Otherwise I would have concluded that it is only transitive. So why transitive now? Why transitive? So I'm saying that A comma B and B comma C belongs to R implies A is greater than B and B is greater than C. B is greater than C. Therefore, can I say that A is obviously greater than C? A is obviously greater than C. Therefore, I can see the ordered pair A comma C belongs to R. Yes, therefore R is transitive. Conclusion is R is transitive. So, tick option C, R is transitive. Tick option C, R is transitive. So that question is very clear? Yes. So let's begin with the next question now. Okay, a very simple question. The relation R in the set N, means natural numbers, given by R is equal to ordered pair A comma B, then which is the relation in this which satisfies, the conditions of A is equal to B minus 2, A is equal to B minus 2, and B should be greater than 6. We just have to look at the options and come to the conclusion. Just look at the options. Which of the pairs where B is greater than 6? So first pair where B is greater than 6 is this. Yes, 8. And the second pair is also this. The third pair is this. Okay. And the difference of B with 2. What is B minus 2, all of you? What is B minus 2 here? 8 minus 2. 8 minus 2 is equal to 6. 8 minus 2 is going to be 6. But this is not 6. So this is wrong. Okay, cannot be 3. Okay, what about this one? Again 8 minus 2, which is equal to 6. Yes, it is 6, right? This is correct. So my answer is going to be option C. My answer is going to be option C. 6, 8 is the ordered pair which satisfies all the conditions given inside the relation R. Easy question. Okay, next question please. Okay, R1 and R2 R1 and R2 are symmetric relations on a set A, then R1 union R2. It's again a property, my dear students. It's a very simple property. If R1 and R2 is symmetric, R1 and R2 is a symmetric relation, then what is going to be R1 union R2? What is going to be R1 union R2? R1 union R2 is also going to be a symmetric relation. R1 union R2 is also going to be a symmetric relation. Direct answer. R1 union R2 is also going to be a symmetric relation. Okay, no doubt in that. If R1 and R2 is reflexive, R1 union R2 is also reflexive. If R1 and R2 is transitive, then R1 union R2 is also transitive. If R1 and R2 is equivalence, R1 union R2 is also equivalence. Keep in mind, the union of two relations will exhibit the same property of the two relations. If you say R1 is reflexive and R2 is symmetric, will the union become reflexive and symmetric? No, that doesn't work like that. Both the relations should be exhibiting the same property. Okay, both of them are reflexive, then the union is also reflexive. Both are symmetric, then the union is also symmetric. Both are transitive, then the union is also transitive. But intersection doesn't do like that. Okay, fine. Direct answer there. Next question, please. R is an identity relation on a set A, then R is reflexive only, symmetric only, transitive only, equivalence. What is meant by an identity relation? What is meant by an identity relation? Very simple. R is an identity relation. R is an identity relation if and only if R is equal to set of ordered pair x comma x such that for every x which belongs to the set A. That is, for every x that is inside the set A, you should only consist of elements containing ordered pairs x comma x. For example, I am saying my set A is equal to 1, 2, 3. Then it becomes an identity relation. It becomes an identity relation IR only if I can have the pairs 1, 1, 2, 2 and 3, 3. I believe everybody remembers this relation, right? We did this in a question where to find the maximum number of equivalence relations that can be formed using the set 1, 2, 3. Your first relation was 1, 1, 2, 2, 3, 3. So 1, 1, 2, 2, 3, 3 formed from the set A is equal to 1, 2, 3. It is obviously reflexive. It is symmetric. It is transitive. I had explained this already before. That's why I said this is a very, very important concept. The equivalence relations that can be formed from a set. So this identity relation is only going to have reflexive pairs, and because only reflexive pairs are there, it is exhibiting the symmetric and the transitive property. So my answer is this identity relation is an equivalence relation. Identity relation is an equivalence relation. Okay, let's go to the next question now. Let R be the relation defined on the set n of natural numbers, and by the rule x plus 2y is equal to 8. The relation between the numbers x and y is x plus 2y is equal to 8. Then the domain of R is, what is the domain of R? Domain means I want the value of x, which makes the answer to be 8 for a value of y. So x is equal to 8 minus 2y. And remember, it's defined on the set of natural numbers. So y is a natural number and x is also a natural number. This is defined on the set of natural numbers. Defined on the set of natural numbers. So y is a natural number and x is also a natural number. So let's try to find out the pairs of natural numbers which is going to be obtained. So if I put y is equal to 1, y is equal to 1. So 8 minus 2 into 1 is equal to 6. 8 minus 2 into 2 is equal to 4. 8 minus 2 into 3 is equal to 2. 8 minus 2 into 4, I'm just putting on natural numbers. Answer is 0, and this is not a natural number. this is not a natural number. Get it? So what is my answer going to be? What is my answer, all of you? The set of numbers 642. The set of numbers 642 or 246 is the values of x. The values of x. The domain, the values of x. Okay, easy answer. Yes, let's go for the next question now. A is equal to ABC and R is equal to AA, BB, BC, AB and AC. Is this relation symmetric? Is it transitive? Is it reflexive? Is it equivalence? Now all of you, my set is A, B, C. My set is A is equal to A, B, C. Is it reflexive? It is not, because I have AA. I have AA here. Yes, you can see I have AA here. Yes, I have BB, but I don't have CC. I don't have CC. C, does not belong to R. C, does not belong to R. So it is not reflexive. Not reflexive. It is not reflexive. So if it is not reflexive, I can obviously reject two options. I can reject option C. I can reject option D. Because option D is equivalence. If it is not reflexive, it cannot be equivalence also. What about symmetric? What about symmetric? Let's see. Look at the pairs. B, C. I have B, C belongs to R. B, C belongs to R. But C, B does not belong to R. C, B does not belong to R. So it is not symmetric. Then I don't have to check. I can say my answer is transitive. I can say my answer is transitive. Okay, you can just check for the condition for transitivity. It's going to be a simple answer. The three options are rejected, the fourth options. Okay, it is transitive. Next question, please. Every relation is a function and every function is a relation. Is it so? What is a relation, all of you? Subset of Cartesian product. Yes, relation is the subset of Cartesian product. Though it is not required here, I'm just saying the definition once again. The relation is a subset of Cartesian product. And what is a function? Function is a special relation. Function is a special relation. I'm not writing the entire definition. Just saying it's a special relation where every element in the domain has a unique element in the range. And every element in the domain has a unique image in the range. Only those kind of relations are considered as a function. So is every relation a function? No. Every relation is not a function. This part of the statement is false. This part of the statement is false. Every relation is not a function. But every function is a relation. Yes, every function, because function is a special relation. So this is true. This is true. Yes, this is true, but the other one is false. So I can say that the statement is a false statement. This saying and over here. Yes, and is mentioned. So every relation is a function and every function is a relation is a false statement. It's a false statement, my dear students. I hope everybody is clear with it. Yes. Okay. Next question. You're defining a relation R in the set of real numbers as A or B. If A is greater than or equal to B, then R is what? An equivalence relation. Reflexive, symmetric but not transitive. Symmetric, transitive but not reflexive. Neither transitive nor reflexive but symmetric. Okay, let's look at it. A greater than or equal to B. Let's look the condition for reflexive. What is meant by reflexive? Ordered pair A, A implies A is greater than or equal to A. Is it true or false? Obviously true. A is either greater than or equal to A. Yes. A is equal to A. It's a true statement. So it is reflexive. It is reflexive. Let's think about symmetric now. Symmetric. So reflexive you can check directly, but whenever I said symmetric, I said not to check whether it is symmetric. I said to check which is not symmetric. If it is not going to be proved to be not symmetric, it is symmetric, right? Yes. So what is the condition now? Let's check an ordered pair. 2 is greater than equal to 1. 2 is greater than equal to 1, but 1, 2 does not belong to R. 2, 1 belongs to R because 2 is greater than equal to 1. But 1, 2 does not belong to R. What is the reason? Since 1 is not greater than or equal to 2. 1 is not greater than or equal to 2. So it is not symmetric. It is not symmetric. It is not symmetric. What about transitive now? I said again, check for not transitive. I said check for not transitive. But this is an easy question for transitivity. So I'll write it directly. A, B and B, C belongs to R implies A greater than equal to B, B greater than equal to C. Therefore, A is greater than or equal to C. It's correct. A is always greater than equal to C, right? Because of the first two conditions. So it is true. It is true. It is symmetric. It is not symmetric. It is reflexive and transitive. It is not symmetric, reflexive and transitive. Option B. It is reflexive, transitive, but not symmetric. It is a simple, direct NCERT question. You can easily by heart it, or maybe you can learn it like this. Okay. A greater than equal to B. Okay, next question. I want to satisfy the condition modulus of A squared minus B squared is less than 7. Look at the options. Modulus of A squared minus B squared is less than 7. I would say option A is wrong. Option A is wrong simply because look at this pair. Look at this pair. They are saying 3 squared minus 1 squared is equal to 8. Less than 7. Wrong, right? 8 is not less than 7. Similarly, reject option B. Reject option B because of this pair. 16 minus 4 is 12. 12 is not less than 7. Okay. Option C, rejected. Why? Because of this pair. Look at this pair. That pair says that 25 minus 16 is equal to 9, which is not less than 7. And the only answer which satisfies all this condition is option D. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. All of them are 0, which is less than 7. 1, 2 is 1 minus 4, which is 3. 2, 3. It's 4 minus 9, which is 5. All of them are satisfying the condition of A squared minus B squared less than 7. So my key condition is modulus of A squared minus B squared is less than 7. Keep that in mind. Your answer is going to be correct. Okay. So let's go to the next question now. Which of the following from Z to Z is a bijection? What is meant by Z to Z? What is meant by Z to Z, all of you? Try to understand what is meant by Z to Z. Means integer to integer. So X is an integer. Then f of x, your y is also an integer. Okay, the domain is integer, the range is also an integer, and is saying to be a bijection. What is meant by bijection? Bijection means it is to be 1, 1 and onto. It is to be 1, 1 and onto. 1, 1 and onto. What is the condition for a function to become 1, 1 and onto? What is the condition for a function to become 1, 1 and onto? 1, 1 means what? What is the meaning of 1, 1? 1, 1 simply means that every element you take from the domain. Yes. So this is going to be the domain. Yes. This is going to be the domain. This is going to be the codomain. 1, 1 means every element you take from the domain will have exactly one image in the range of. Yes, and a unique image. That is, this image y1 should belong to only x1. There should not be any other element. If I take any other element x2, it should not go to y1. it should not go to y1. That is the condition for becoming 1, 1. If it goes to y1, it is not 1, 1. So look at this answer. F of x, if I put a value for x over there, whatever I put for x, I will get a cube, x cube. Okay. Now tell me, is there any two numbers x which gives me the same answer for x cube? Whether you put positive or negative, x cube is going to be always unique. X cube is always going to be unique. So it is 1, 1. This function over here is 1, 1. This is 1, 1. This is 1, 1. Right? F of x is equal to x cube is 1, 1. Is it on 2? Is it on 2? That is the problem. Check whether it is on 2. What is the meaning of on 2? What is meant by on 2, all of you? On 2 means the same explanation here. On 2 means that if I have a y here, y1 here, y2 here, a y3 here, I'm just saying an example, there should always be an x. There should always be an x which is the pre-image of this y. And if I have a y which does not have a pre-image, no pre-image, then f is not on 2. Then f is not on 2. I believe everybody knows the theory. Yes. When you have a y in the codomain which does not have a pre-image, then f is not on 2. Okay, now look at this condition over here. I have a x cube here. So let's try to understand. F of x is equal to x cube. F of x is equal to x cube. And then this x is going to be the cube root of f of x. Cube root of f of x is not always an integer. This is not always an integer. Okay, not always an integer. For example, if I say I'm trying to find the cube root of 2, the cube root of 2, it's not an integer. The cube root of 2 is not an integer. So it is not on 2. So 1, 1, not on 2. 1, 1, not on 2. So bijection means it should be 1, 1 and on 2. Okay, now look at second option. F of x is equal to x plus 2. Now you can just look and tell. If I put an integer for x, x plus 2 is also going to be an integer. So it is 1, 1, unique integer. Every x is going to have a unique integer. Okay, fine. Now think backwards. F of x minus 2. Think backwards. F of x, option B. F of x is equal to x plus 2 implies x is equal to f of x minus 2. So whatever integer I put for f of x minus 2 is also an integer. There is no situation where I'm not getting an integer for x. So every f of x has a pre-image. Every f of x has a pre-image. So this is a function which is both 1, 1 and onto. This is a function which is both 1, 1 and onto. Okay, so you can use the basic definition for 1, 1, or just observation is more than enough for this question to tell whether it is 1, 1 or onto. You have a definition for 1, 1, right? If f of x1 is equal to f of x2, then I have to prove that x1 is equal to x2. This is the condition for checking whether a function is 1, 1. Okay. Now with this question, we have completed the discussion of the part 1 questions of chapter 1. So we'll be coming back with part 2 again. We have few more questions to discuss. We'll be coming back with part 2 again. Thank you everyone.